Assalamu alaikum. Bismillahirrahmanirrahim. I welcome you to the 18th lecture for the series of lectures on advanced computer architecture. Today, our focus of discussion will be hardware-based speculation. Last time, we discussed three basic concepts to accomplish multiple instruction issue. These concepts included branch target buffer, integrated instruction fetch unit, and return address predictor. While talking about branch target buffer, we said that it is a technique which provides the target branch address at the instruction fetch stage. We further discussed the enhancement in branch target buffer technique, and we introduced the concept of branch folding, which stores or buffers the branch target instruction instead of branch target address. Both these techniques, that is the branch target buffer and branch folding, facilitates us to reduce the number of stalls, or if branch is predicted correctly, then it eliminates the stalls which may occur otherwise to control the control hazards. The method used for described in integrated instruction fetch unit was that here we combine three different features, that is the branch prediction, instruction prefetch, and instruction memory address and buffering at one stage in one unit, and we perform these operations at the instruction fetch stage. Then we also talked about the return address predictor, which is one which is used for indirect jump instructions. For example, the indirect procedure call or case statements or select statements, we use this concept to reduce the number of stalls and to control the control hazards. After introducing this basic concept of controlling the number of stalls to overcome the control hazards, we talked about two different variations of multiple issue, which means multiple instruction issue processors. These two versions are known as the superscalar processors and very long instruction word processors. In the superscalar processor, we said that multiple instructions issued in one clock cycle are scheduled either statically or dynamically, whereas the very long instruction word processor schedule multiple instruction issues in one clock cycle using static approaches, that is by using the compiler. We also talked about the performance enhancements and limitations imposed onto the static and dynamic scheduling techniques for superscalar processors. Last time, while discussing a loop-based example, we observed that the control hazard which prevent us from the next iteration, it causes a 1 cycle delay before we take a decision whether the branch is taken or not taken. This limitation is taken up by another technique known as hardware-based speculation. Today, we will focus our discussion onto this hardware-based speculation technique, and we will discuss how we can apply this technique for resolving the issues and minimizing the limitations which we have discussed so far for multiple issue processors. The hardware-based speculation offers many advantages, such as it can incorporate hardware-based branch prediction. It does not depend upon the compiler, and it does not require any additional bookkeeping. This concept of hardware-based speculation has been implemented in a number of systems, such as the PowerPC 620, MIPS R10000, Intel P6, and AMD K5, etc. Here we have observed that the exploitation of more instruction-level parallelism enhances the burden of maintaining the dependence, wherein the branch predictor reduces this burden, and it reduces the number of stalls to deal with the branch operation. Therefore, while exploiting the instruction level parallelism, we require to overcome the limitations of control dependence. These limitations of control dependence can be overcome or minimized by using hardware speculation techniques. Here, in the hardware speculation, we fetch, issue, and execute instructions as if our branch predictors were always correct. We know that the dynamic scheduling without speculation fetches and issues, but it does not execute such instructions until prediction is found to be correct. So the main idea in hardware-based speculation is to allow execution of an instruction dependent on a predicted as taken branch, such that there is no consequence, including exceptions such as memory violation if branch is not actually taken. Further, we don't want a speculative instruction to cause exceptions that stop programs. For example, the memory violation, etc. This can be achieved if hardware support for speculation buffers the result and exceptions from instructions until it is known that the instruction would execute. This shows that the hardware-based speculation combines three basic concepts. The three key concepts which are combined over here are the dynamic branch prediction, speculation, and dynamic scheduling. We will be talking about these one by one now. The dynamic branch prediction facilitates to choose which instruction to execute, that is, which instruction is the next, that is, whether it is the instruction in sequence or it is the branch instruction. The second step, speculation, it deals with to speculate to allow the execution of the instruction before the control dependence is resolved. Here, the hardware has the ability to undo the instructions which has already been done, and if there is any exception. The third concept used over here is the dynamic scheduling. The dynamic scheduling deals with the scheduling of different combinations of basic blocks. Thus, the hardware-based speculation follows the predicted flow of data values to choose when to execute. In order to do so, we must separate the bypassing of results among instructions, where bypassing is needed to execute an instruction speculatively, and we have to separate this bypassing from the actual completion of the instruction. By making this separation, we can allow an instruction to execute and to bypass the results to some other instruction without allowing the instruction to perform an update that cannot be undone until we know that the instruction is no longer speculative. When the instruction is no longer speculative, we allow it to update the register file or memory. This additional step in the instruction execution sequence is called instruction commit. This shows that the basic idea behind implementing the speculation is to allow instructions to execute out of order, but force it to commit in order. In a single issue 5-stage pipeline, we can ensure that the instructions are committed in order simply by moving writes to the end of the pipeline. Because when we add speculation, we need to separate the process of completing execution and instruction commit, as the instructions may finish execution considerably before they are ready to commit. So this way, adding this commit phase to the instruction execution sequence requires some changes to the sequence, as well as an additional set of hardware buffers that holds the result of instructions that have finished execution but have not yet committed. This additional set of hardware buffers is known as reorder buffers, which is abbreviated as ROB. It is shown over here in this block diagram, which gives us the modified versions of the Tomasello's earlier hardware, which we discussed for dynamic scheduling last time. Here, the reorder buffer can be operand source if values not yet committed. This means that if the values have not yet been committed, then the operands can be obtained from reordered buffer. Once operand commits, the result is found in register file. The mechanism of this modified hardware is that at the issue time, it allocates an entry in the reorder buffer to hold the results. As each value has a location in the reorder buffer, therefore, it uses the reorder buffer entry number instead of reservation station to rename any variable. However, we can use additional registers for renaming and the reorder buffer only for tracking the commits. Instruction results committed to the register set in order. If reorder buffer is implemented as a queue, then it is simple to undo speculated instructions on mispredicted branches, or on exceptions, just require throwing away uncommitted entries. The exceptions are not recognized in this structure until an instruction becomes ready to commit. The figure shows here the Tomasulo's hardware structure, including the reorder buffer. Here, the basic structure of MIPS floating point unit using Tomasulo's algorithm is extended to handle speculations. The mechanism may be further extended to multiple issues by making a common data bus wider to allow multiple completions per clock. Here, the reorder buffer provides additional buffer same way as in the reservation stations in Tomasulo's pipe that extends the register set. The reorder buffer holds the results on an instruction between the time operations associated with the instruction completes and the time instruction commit. Hence, the reorder buffer is a source of operands for instructions, just as reservation stations provided operands in Tomasulo's algorithm. In Tomasulo's approach, once an instruction writes its result, any subsequently issued instruction will find the results in the register file. Whereas in speculation, the register file is not updated until the instruction commits. Thus, the reorder buffer supplies operands in the intervals between completion of instruction execution and instruction commit. The reorder buffer is similar to the stores buffer in Tomasulo's approach. The reorder buffer consists of 4 fields. These fields are the instruction type, the destination, value, and ready. Let us discuss these fields one by one. The instruction type field indicates whether the instruction is a branch and it has no destination. The instruction is a store which has a memory address destination, or third, the instruction is a register operation, ALU operation, or load operation which has register destination. The destination field supplies the register number for load and ALU operations, or it supplies the memory address for store where the instruction result should be written. The third field, the value field, is used to hold the value of instruction results until the instruction commits. Whereas the last field, ready, indicates that the instruction has completed execution and the value is ready. Considering these four basic fields of the reorder buffer, now let us see that how the Tomasello's algorithm is to be modified to implement speculation. The Tomasello's algorithm is modified by introducing another step instead of its original 3 steps. As you know, the original steps which we discussed earlier are the issue, the execute, and write result. Whereas in modified Tomasello, the 4th step is commit. So let us review what are these 4 steps and what are different actions which are taken in these 4 steps. In the issue stage, it gets instructions from the head of the instruction queue. If reservation station and the reorder buffer slots are free, then it allocates and issue the instructions. If it is not free, then it is stalled. If operands are available, then send them to the reservation station. Otherwise, it keeps track of the reorder buffer entry that will produce the operands. During the execute stage, it operates onto the operands. If both operands are ready, then it executes. Otherwise, it watches the common data bus for result. Then it checks the read after write hazard, and the instruction may take multiple cycles here before it is completing its execution. The third stage, which is the write result, this stage is one where the execution stage finishes. The values are to be written back. The values are made available onto the common data bus, and the reservation station is marked. If the value to be stored is available, then it is written to the value field of the reorder buffer entry for the store. If the value to be stored is not yet available, then the common data bus must be monitored until that value is broadcasted, at which time the value field of the reorder buffer entry of the store is updated. The last stage commit can occur when an instruction reaches the head of the reorder buffer and its result is present in the buffer. It updates the register with the reorder buffer result, or it send or store to memory and free up the reorder buffer slot. Here, if reorder buffer head is an incorrectly predicted branch, then it flushes out the reorder buffer. If the branch was correctly predicted, then the branch is finished and the value is committed. Now I will discuss the use of hardware-based speculation to enhance the performance of single issue and multiple issue pipeline using Tomasello's approach. For this purpose, I will consider the same example as we considered earlier while explaining the basics of dynamic scheduling. The example program is shown here, where you can see that the first two instructions are load instructions. The next instruction is multiply, then it is followed by subtract, divide, and add instructions. We will be considering this example to explain how the modified versions of Tomasello's pipeline for speculation enhances the overall performance of the system. For this purpose, you can see that in the tables shown over here, we are making certain assumptions while drawing these tables, and these assumptions are as follows. The value column indicates the value being held. The format #x is used to refer to a value field for reorder buffer entry x. Furthermore, we are assuming that the latencies of different types of instructions are the same as we considered in our earlier examples while talking about dynamic scheduling. If you recall, at that time we used the latency for add instruction to be equal to 2 clock cycles, for multiply instruction to be equal to 10 clock cycles, and for divide instruction to be equal to 10 clock cycles. Now let us analyze this table and see how this table is working when we are using hardware-based speculation implemented in the Tomasello's pipeline. Here you can see that although the subtract instruction has completed execution, it does not commit until the multiply instruction commits. Furthermore, the reservation stations and the register status field, they contain the same basic information as they contained for simple dynamic scheduling while using this Tomasello's algorithm. This is quite clear from this comparison of the two tables shown over here. You can also note here that at the time multiply is ready to execute and only 2 load instructions have committed, although several other have completed the execution. The subtract and add instructions here will not commit until the multiply instruction commits, although the results of the instructions are available and they can be used as source for other instructions. Furthermore, here the divide is in execution, but it has not completed solely due to its longer latency than the multiply instruction. Comparing these two tables, you can see that in the earlier version, that is the implementation of Tomasello without speculation, the add and subtract instructions completed out of order. That is, they completed before the multiply instruction completed. But in case of the revised version with speculation, the case is reverse. Furthermore, the other differences are that the reservation station numbers are replaced with reorder buffer entry number in QJ and QK and in register status fields. Moreover, the destination field is added to the reservation station. The destination field designates the reorder buffer number that is destination for the result. So far, we have been talking about the use of speculative processor for single issue instructions. Now let us consider the case of multiple issue with speculation. As speculative processors can be extended to multiple issues using the same technique as applied when executing Tomasello-based processing. There are two challenges for the multiple issues in Tomasello algorithm. These challenges are, number one, instruction issue and monitoring the common data buses for instruction completion. And second is maintaining throughput of greater than one instruction per cycle. To show how speculation can improve performance in a multiple issue processor, we will consider an example here. Now, in this example, let us consider the execution of the same loop-based example which we considered for simple dynamic scheduling. Now, this example searches an array on two-issue processor, one without speculation and once with speculation. And let us see that how these results differ from each other. In order to discuss this particular example, we will make certain assumptions. The one major assumption is that we assume that there are separate integer functional units for effective address calculation and for ALU operations. And there is a separate integer functional unit for branch condition evaluation. Furthermore, we also assume that up to 2 instructions of any type can commit per clock cycle. This is the major assumption which makes the case different from single instruction per cycle. Let us consider these two tables for the first 3 iterations of this loop for machine with speculation and for the machine without speculation. The table for machine with speculation is the same as we considered earlier, but this table with speculation has been redrawn. over here. The first table shows the time of issue, execution, and writing result to two issue dynamically scheduled processors without speculation. Here, note that the load instruction following the branch not equal cannot start execution earlier because it must wait until the branch outcome is determined. This type of program with data-dependent branches that cannot be resolved earlier show evaluation allow multiple instructions to execute in the same clock cycle. Here you can see that the second table shows the time of issue, execution, and writing results for a dual version, that is two issue version of our pipeline with speculation. Here, note that the load following the branch not equal can start execution earlier because it is speculative. Comparing the two tables, you can note that here the third branch in the speculative processor executes in 13 clock cycles, while in the non-speculative processor, it completes execution in 19 clock cycles. So this shows that the non-speculative pipes are falling behind the issue rate rapidly as compared to the speculative processors. Now, with this much discussion on to the hardware-based speculation and its applications for single issue instructions and its use for multiple issue instructions, here we have observed that the performance of dynamic scheduling with speculation is much better as compared to the performance of dynamic scheduling pipeline implementing the Tomasello's algorithm for non-speculative applications. So far, we have been discussing the enhancements in Tomasello's structure to handle speculations in single issue, and then we talked about speculations in multiple issue processors. Here we observed that the store buffer of Tomasello's structure have been eliminated, and it has been replaced by using a reorder buffer that incorporates the function of this store buffer. The structure is also further extended to handle the multiple issue instructions. Now we will talk about those exceptional cases which may arise when executing a program using dynamic scheduling, but by using the extended version of the Tomasello's structure to take care of speculations. We know that the dynamic scheduling using Tomasello's structure without hardware speculation allows to complete the execution of instruction in order, whereas the modified structure with hardware-based speculation, it commits in order. This shows that if an exceptional situation occurs while executing an instruction, then the reorder buffer in the structure with speculation does not commit, and it handles the exceptions first, and then it takes a decision. We will discuss this and explain this by reconsidering our earlier examples, where we found that the Tomasellos structure with speculation and without speculation, it executes in a different way. In this example, as you can see from here, the instructions subtract and add occurring after the incomplete instructions multiply, but they executed earlier, do not commit until the instruction multiply completes and commit. Therefore, in an exceptional case, if multiply causes an interrupt, then this interrupt is handled as follows. We can wait until the interrupt reaches the head of the reorder buffer and any pending instruction is flushed out. The speculation is undone. Whereas in case of dynamic scheduling without speculation, the results in registers F8, which is for subtract instruction, and in register F6, which is for add instruction, they could not be overwritten out of order. Thus, the interrupt could not be handled in this case. Further, the exceptions are handled by recognizing then until it is ready to commit. I will discuss this and explain this with the help of our earlier example, which we discussed while talking about the Tomasellos structure for dynamic scheduling, which is for a loop example. This example is reproduced over here. If an exception arises, say due to interrupt from the multiply, the exception is recorded in the reorder buffer. At the same time, if misprediction arises from the speculated instruction, that is the branch if not equal, then the exception is flushed out along with the speculated instruction that should not have been executed when the reorder buffer is cleared. Now today I have been talking about the hardware-based speculation. Then we discussed the modifications in the circuit for handling the hardware-based speculations. The focus of our today's discussion has been the modifications in Tomasellos hardware to handle speculations as well as to handle exceptions. While talking about the speculation, we said that speculation on the outcome of branches is made to avoid control hazards which prevent us from starting the next operation before we know whether the branch was correctly predicted or not. The main idea behind this whole discussion was that it allows us execution of a branch instruction predicted taken such that there is no consequences if branch is not actually taken. Furthermore, we do not want a speculative instruction to cause exceptions which stop the program. While talking about this, we said that the software-generated interrupts or the memory violations are typical examples of exceptions. Here we found that this can be achieved by including a buffer that holds the result as well as exceptions from the instructions until it knows that the instruction will commit. Such a buffer is known as a reorder buffer, which is used only to track commits. The reorder buffer is flushed out if the speculation does not hold or exception is found. With this much discussion, on to the hardware-based speculation, we have in fact covered almost all concepts which are used for dynamic scheduling in order to achieve high performance in instruction level parallelism. We have been talking about the Tomasello's approach to handle single issue of instructions, and then we also talked about the multiple issue scenarios where we found that the Tomasello's structure is giving us high performance. Then we also considered different examples, and in these examples we discussed how we can make use of prediction approach to handle stalls in avoiding the control hazards. We also discussed over here number of other techniques to take into consideration the performance enhancement by dynamic scheduling of instructions in a pipeline architecture. So before I conclude at this stage today, next time we will take into consideration what are the practical limitations which may exist while implementing this type of dynamic scheduling, and we will also take some real-time examples of different types of processors, and we will discuss about their performance. All these examples will be considering the dynamic scheduling and hardware-based speculation implemented over there. With this much discussion today, I will stop here and I say you Allah Hafiz.